Swayam Prabha. Digital India. Educated India.
So, today we will see some more applications of friction. For your reference, this is module 5, lecture 12 of the engineering mechanics course. In the previous lectures, we saw some applications like the screw jacks and thrust bearing. Today we will see the application of friction in journal bearings, and also we will see how rolling resistance and wheel friction are induced in the motion of wheel. So, in this picture you see an axle supporting say pulleys which are driven or driving some machineries. So, this is the way commonly these pulleys are supported. So, these are the axles, and the axles rotate about this axis, which has to be supported by the end bearings. So, the motion is in the horizontal, and so the radial forces, the weight of this pulley and other forces are radially transmitted to these bearings, which have to be supported by this bearing block at these two ends. We have already seen one kind of bearing, that is the thrust bearing, which provides axial support. So, these bearings are known as journal bearings, which provide lateral support to the rotating shaft. To reduce friction, lubrication is generally applied between the axle and the bearing block. So, the frictional resistance that occurs between the axle and the bearing block depends on many factors, primarily the clearances between the axle and the journal block, the speed with which the shaft or the axle is rotating, and the viscosity of the lubricant that is being used. Partially lubricated bearings can be assumed to be existing in dry condition, and one can assume that the axle is having a point contact, or along the bearing it is having a line contact while in motion. So, with this assumption we will proceed how to analyze this problem. So, this figure shows the pulley which is being supported by this axle, which is supported by this bearing block. So, this circle shows the bearing surface where the axle is in contact with the bearing block. Let us say W be the weight of these pulleys or wheels that are being supported by this axle, and a moment of M is being applied to keep this wheel in motion. So, the reaction from the bearing to the axle has been shown to be shifted to a location which is not the point of contact if the wheel is stationary. So, let us see how this actually happens. Let us consider this wheel and the axle being supported by this bearing block. So, for clarity, let this be the weight W that is being applied to this bearing block through this axle. When the wheel is stationary, the point of contact is here. If we exaggerate the situation that there is a clearance between the journal and the shaft or axle. So, this is the clearance that you see, and when the shaft is idle or not in motion, the point of contact is here, or along the journal. This is the line of contact between the axle and the journal. This is the weight that is being carried by this axle. So, the support reaction from the bearing block acts at this point, let it be R. When, let us say, we give a small rotation to this axle, then because of the friction that exists, the axle climbs the journal. Because no slippage occurs at this point, and with respect to this point, this axle tends to move, and so new points of contacts happen, and slowly the axle tries to climb in this direction. So, the point of contact actually shifts, and this happens till some maximum point which corresponds to the impending slippage case, where the normal reaction is like this. Since the shaft or the axle is tending to slip in the downward direction, this is the direction in which the axle is trying to slip. So, the friction will be acting in this direction. So, this will be the frictional force, and this will be the normal reaction, and the resultant of this two will be R, and this value reaches the maximum limiting value, where this frictional force F is related by this N by the coefficient of static friction. And once the journal starts rotating at some higher speeds, the point of contact slightly comes down, because the kinetic friction is lower than the maximum static friction, and so the point of contact shifts from this, let us say, the maximum point up to which the axle has climbed, to another position, and it remains in equilibrium at this position. So, that is what is represented in this picture. For a constant motion of this axle, the point of contact has shifted from say the lowest point A to the point B, and this is the frictional force, which is the kinetic frictional force existing between the axle and the journal. This is the normal reaction along the radial line, and the resultant of this two is R, which is vertical and equal in magnitude to that of W. So, the moment or the couple of these two forces, equal forces, that is W and R, has to be balanced by the applied moment, else this couple, which is anti-clockwise, will retard the motion. That means the wheel, which is, let us say, revolving or rotating, it will come to stop if this M is not applied. So, to keep this wheel in constant motion, this moment M has to be applied, the clockwise moment of M has to be applied. So, we call this as the frictional moment that has to be overcome in the journal bearings. For this equilibrium position, we know the angle between the resultant and the normal force is phi k, which is angle of kinetic friction. So, certain things you can again observe, that reaction is vertical and is equal to the magnitude of the weight carried by the axle. The line of the reaction, which is passing through this B, does not passes through the shaft center, that is O, which is the case when the shaft is idle. So, the reaction passes through O when the shaft is idle, but now it has been shifted to a location because of the motion of the axle. So, here for this case R is located to the right of O, because the axle tends to climb in this direction. If the wheel is rotating in the counterclockwise direction, that is the applied moment was counterclockwise, then the wheel will climb in the other direction, and so this point of contact B will be to the left of O, but in this case it is located to the right of O. This results in the moment, and which is balanced by this applied moment. So, this is what we call that physically the axle climbs in the bearing. So, this picture just shows the various forces and the moments that are acting. The angle between R and the normal, as we have seen, is phi k, and so we can write the moment caused because of this resultant R as R times small r, which is the radius of the axle, times sine phi k. So, which is nothing but the horizontal distance of displacement of this point of contact B. So, this distance is R sine phi k. For small angles of phi k, we know that sine phi k is equal to tan phi k. This is because tan phi k is nothing but sin phi k divided by cos phi k, and for very small angles this cos phi k is nearly 1. So, this can be approximated for small angles, and that is why we write this is approximately equal to r times r tan phi k. And we know that tan phi k is nothing but the coefficient of kinetic friction, and so we replace this by mu k, and we see that this moment m is equal to r times small r mu k, where r is the reaction force which is equal to the weight w, and r small r the radius of the axle, and mu k is the coefficient of kinetic friction that exists between the axle and the bearing block. So, we can treat this bearing reaction R at this point B as a force and a couple system. So, let us see how to do that. We have this wheel and the axle, the weight passing through O, and the point of contact has shifted to this point B. This is the normal reaction, and we have the frictional force and the resultant R. This is small r, the radius of the axle. Now, I can replace this resultant force R by a force that passes through point A, which is the lowest point of contact, or which is just below O, the center of the axle, and replace this by a force R and the moment due to this force being acting at this point B. So, this can be replaced by this force R and the moment. So, this is the force R acting at A and a moment m which is equal to R sin phi k, which we just found. It is approximately equal to R times R mu k. So, we can treat this reaction R at B as a reaction R at A and a moment. Graphical solutions are possible where we can place this reaction force R tangential to the circle, which we call it as the circle of friction, because we have seen that this R is displaced by a distance equal to R sin phi k. So, this vertical displacement is equal to R sin phi k, which is approximately equal to R times mu k. So, I can draw the free body diagram with this reaction R such that it passes tangentially to the circle of friction whose radius is Rf, which is given as R mu k. Let us take one example problem and see how we solve the problem of this journal bearings. Here you see a pulley supported on a shaft at O. The diameter of the pulley is given as 400 mm and it can rotate about the fixed axis shaft of diameter 200 mm. So, this axle or the shaft is having a diameter of 200 mm. This is 200 mm and this has been given as, this is the radius. So, we have it as 200 mm and the diameter of the pulley is given as 400 mm. The coefficient of static friction between the pulley and the shaft is known as 0.2. We are interested to determine the smallest vertical force P required to start raising a 500 Newton load. So, we have this 500 Newton load attached to a belt passing over this pulley and this force P is being applied in order to raise this. We are interested to find the smallest vertical force that will be required to raise this load, and secondly we are interested in finding the smallest vertical force P that will be required to hold the load. That means, if we will leave this, the weight will fall. So, we need to keep some resisting force P so that this load does not drops. So, here we assume that the impending slippage does not happens between the belt and the pulley, but rather the slippage occurs between the pulley and the shaft. So, the slippage is on this surface and not on this surface. So, for the first case, let us draw the free body diagram. When this P tends to lift this weight W, the impending motion is clockwise. That means, this pulley tends to move in the clockwise direction over the axle or the shaft. So, the point of contact which is originally at A now shifts to B and it tends to slip at this point B. This can be found by considering the analogy that we have the axle and the pulley. Originally the point of contact is at A, and as the pulley tends to move in this direction, for exaggeration let us keep that this is the diameter of the shaft. The point of contact slowly shifts in this direction, and once it reaches some maximum value, it starts to slip and the pulley starts to rotate with respect to the axle. So, now we can represent the resultant R, which is nothing but the resultant of the normal force and the frictional force. So, this R is the resultant of the frictional force and the normal force acting at this point, which is, since the slippage is in this direction, the force will be acting in the opposite direction. So, if we want to solve this problem by the graphical method, we can place this reaction R at a distance which corresponds to the radius of static friction. So, the angle made by this R with respect to the normal is phi s. So, we find the radius of friction as R sin phi s, because here it is an impending slippage case, and so we take the coefficient of static friction. So, the radius of the circle of friction will be R sin phi s for small angle, which is equal to R tan phi s or R mu s. So, for the particular case we find this as 20 mm. So, the reaction R is shifted by 20 mm to the right from O. So, we have these distances as 200 minus 20, which is 180 mm, and this distance between this vertical force W and R is 200 plus radius of friction, which is 220 mm. Now, we can sum the moments about B and equate it to 0 for equilibrium. So, we have the moment arm for this 500 Newton force as 220 mm and the moment arm for the force P that is used to raise as 180 mm. So, we have 220 into 500 minus 180 into P equal to 0, from which we find P as 611 newtons. For case B, we are interested to find the force P that is required to just hold the weight. So, that means now the impending slippage is that the pulley starts to move in the counterclockwise direction. So, the point of contact, which is originally at A, now shifts in the counterclockwise direction to a point C, where the horizontal displacement of this reaction R is equal to the radius of the static friction circle. So, which is again 20 mm. So, we see that the moment arm for this weight W is 180 mm and for this force P as 220 mm. So, now we sum the moments with respect to C in order to find this force P required to hold this weight. So, summing the moments, we have the moment arm for the 500 Newton force as 180 mm. So, we have 180 times 500 Newton minus 220 the moment arm for this force P, which is a clockwise moment. So, negative equal to 0. So, from this we find the value of P as 409 newtons. So, this problem illustrated how we can solve the problems involving journal friction by first finding the radius of the circle of friction and then displacing the reaction tangential to the circle of friction and then solving the problem. Now, we will move on to discuss wheel friction or the kinds of friction that occurs when wheels move on platforms. So, in this picture you see a wheel supported in an axle at O. Let W be the weight of the wheel acting through the axis of this axle O. When the wheel is idle, the normal reaction from the ground N passes through this point A and the wheel is in equilibrium. Now, when this wheel starts moving in the forward direction, we know that there exists a friction between this axle and the wheel which resists the motion. So, if the wheel tends to move by rotating in the clockwise direction, then we have the resisting moment acting in the counterclockwise direction at the axle. So, that is what is marked here as M. So, this frictional force that is existing in the, or the frictional moment existing in the axle and wheel prevents this motion in the forward direction. So, in order to sustain this motion or the forward motion, we have to apply a force on the axle. So, that is what is marked as P. In order to overcome this moment M such that if R is the radius of the wheel, then we find that if we apply a moment which is equal to P times of R, then we can sustain this motion. But from the free body diagram, we see that if this force P acts at the axle, then we need a force F at this point A, then only the system will be in equilibrium. We can see that W is balanced by N, the moment M is balanced by the moment due to this force P, that is P into R, but when we sum the horizontal forces, if this force F is not there, then this force P is unbalanced, and in that case what will happen is, rather than rolling, this wheel will start sliding and this point of contact will start just moving like this. So, in order that this wheel is able to roll, we need to have this force F, and that is how this frictional force helps in the rolling motion. So, even though we see that there is a point contact, the presence of friction is necessitated for the rolling action to take place. So, that is what we say, that the moment M due to the frictional resistance of the axle bearing requires the couple produced by the equal and opposite P and F. So, thus the presence of F is necessitated. Without the friction on the rim, that is at this point A, the wheel would slide. Now, let us consider a free wheel which does not has an axle. So, here you see a free wheel which does not has an axle which is tending to roll, and assume that the contact at A between the wheel and the ground has no relative motion for the wheel to roll, because for this rolling action the point A will be idle and the other parts of the wheel will rotate with respect to this point of contact A. So, if the surfaces are hard, then the point of contact or this contact is a point or line along the width of the wheel. So, ideally we see that there is no friction. So, when a free wheel, that is a wheel which is not supported by an axle and which is hard, and the ground on which it rolls is also hard, so that a point or a line contact can be maintained, should ideally roll without stopping if a small rolling motion is given to the wheel. But we see that this generally does not happen for real systems. That means we have a real material constituting the wheel and the ground. Then we see that when a wheel is rolled on the ground, after some time it comes to a rest. So, we can see why this happens, and this happens because of the presence of rolling resistance. Let us see how this rolling resistance comes into picture. In the ideal contact, both these bodies are deformable, and so the point of contact is no longer a line, but rather if this is the weight of the wheel passing through its center. So, we have a region of contact, or in other ways a surface of contact, and thus the reaction is no longer a point force, but rather a distributed force. The resultant of all these forces is equal to this R or N. So, the resultant of all these forces is equal to N, which is equal to the weight of the wheel when this wheel is idle or which is not in the rolling motion. But when the wheel tends to roll, the pattern of these uniformly distributed forces changes. This can be explained by considering the same wheel. Now, let us say the wheel tends to move in the clockwise direction. So, what happens? The contact that is there in this vicinity experiences a compression because of this wheel. We are assuming the ground as well as the wheel to be constituting of materials which are deformable under the action of these forces. So, the material here compresses and thereby offers more reaction, and the material here is relieved because the wheel is moving away from this portion. So, what happens? The distribution here, the material gets relieved and here it gets compressed because of this motion. So, the reactions here are more than the reactions that are in this place. So, the distribution becomes something like this. So, we see that if we take the resultant of all these forces, now it will no longer be this vertical force N, but rather a force which acts at some distance away from the original point under consideration below, say O. So, now this reaction force still passing through O, but having a displacement in the direction in which the wheel tends to roll. So, this point of contact now would have shifted by a distance, say b. So, that is what you see in this picture, that the resultant of these forces have shifted from the point vertically below the axle or the center of the wheel to this point B, whose horizontal displacement is B. Now, the moment due to this force, the vertical component of this force R is balanced by W, but the horizontal component of this R is balanced by this applied force P, which keeps this wheel in rolling motion, and the moment of this force balances this moment of this reaction. So, we see that the resistance to rolling comes because of the moment of this reaction force R, which has to be balanced by an applied moment. So, if this force does not exist, then the wheel comes to a rest because of this resisting moment, the moment due to this force R. So, we see that the reaction is applied at B and P is required to balance the moment of W about B or R with respect to this O or the vertical axis. So, we see that the moment of this weight is W times B, the horizontal displacement of this point, which has to be equal to the moment due to this force P times the moment arm, which is say this point A. So, O A. But for small deformation, we can say that this distance OA is equal to the radius of the wheel itself. So, this is approximately equal to P times of R. So, if the surfaces of contact are deformable, then we need to have this force P in order to keep this wheel in the rolling condition, and this distance B to which this reaction R has displaced from the vertical is known as the coefficient of rolling resistance, and we can easily see that this has a unit same as the unit of length. We know that the coefficient of friction does not has any unit, but the coefficient of rolling resistance has the unit of length. Let us see one example problem. Here you see a vehicle which is having a weight of 65 kilonewton and it is designed for slippery tracks. Say it could be a vehicle that moves on ice or it could move on steel racks, where the coefficient of friction between the wheels and the track is very low, say 0.005. The coefficient of rolling friction is known to be 0.8 mm. The vehicle has 4-wheel drive. That means all these wheels propel this vehicle forward. So, we have 2 wheels in the front and 2 wheels in the rear. So, all these wheels are propelling this vehicle forward and thrust is developed on all these 4 wheels. We are interested to find whether the vehicle will be able to move or not. In order that the vehicle moves, the thrust developed by this wheel should be less than the maximum friction that is available between the wheel and the track. This can be seen by considering this picture of the wheel, and let us say this is the axle on which this vehicle is supported, and we have the track. So, this wheel is developing a moment in order to, or the thrust in order to propel this vehicle forward. So, this will in turn be experienced as a force at this point, and this point will tend to slip in this direction. But to prevent this point from slipping, the friction acts in this direction. We have the normal force. Let us say some component of this weight is being transmitted by this axle through this wheel. We see that we have 4 wheels, so this load will be distributed by those 4 wheels, and if say we have this as the normal reaction, then this frictional force F prevents the wheel from slipping at this point. So, how large this thrust could be? It could be maximal equal to the limiting value of friction at this point, because beyond which this point will tend to slip. So, if this point does not slips, then because of this the axle will experience a forward force, and thus the vehicle will propel. So, the forward motion of the vehicle depends on the fact that the developed thrust force is less than the maximum available friction, and this developed force for traction should overcome this rolling resistance. So, we have to ultimately see that the rolling resistance has to be less than the maximum available friction on the track. If this condition is satisfied, the wheel will be able to propel forward. If the rolling resistance is more than the available friction, then the vehicle will not be able to propel, but rather the wheels will keep revolving, and it will be slipping from the track, and the vehicle will be idle and it will not get propelled. So, let us go to the problem. So, this shows the various forces that are acting. Let us say N1 be the total of the reactions both because of the 2 wheels in the rear, and N2 be the sum total of the 2 wheels that are situated in the front, and the frictional forces that will exist or that can exist to the maximum is mu times of N1. So, this is the maximum value of frictional force that can exist at this point, and same way the maximum value of the frictional force that can exist between the wheel in the front and the track is limited by this value mu times N2. So, we know this geometry, that is the location of the CG of this vehicle, that is it is located at 1.2 meters from the rear axle and 1.3 meters from the front axle and 1 meter from the ground. So, we write the equilibrium equation. Let us say we take the moment summation about this point 1. The moment arm for this reaction force N2 is 1.2 plus 1.3, which is 2.5 meters, minus the moment due to this weight 65 kilonewton force, which has the momentum of 1.2 meters. So, from this equation we find this normal reaction N2, and from force summation equation we can find N1. So, we have this N2 as 31.2 kilonewton, and we write the force summation in the y direction. So, we have N1 plus N2 should be equal to 65 kilonewtons, and from that we have N1 as 33.8 kilonewtons. So, once we have found this normal reactions N1 and N2, we can find the limiting value of frictional forces that are available at the points of contact between the wheels and the track. So, we find the total traction force that can exist without slipping is mu N1 plus mu N2, that is mu times N1 plus N2, which is equal to 0.325 kilonewtons. So, this is the maximum frictional force that is available, and so the traction force cannot exceed this value. So, let us see what is the rolling resistance and see whether that is less than this maximum available traction force. Now, these vectors represents the rolling resistance that has to be overcome, because when this wheel tends to move in this direction, the point of contact shifts to this side when this wheel tends to move in this direction, and so this is the rolling resistance or the force which is acting from right to left, which has to be overcome. So, we will find this to be equal to the total weight or the normal reaction, because this is equal to W times of B by R, where W is the load that is being carried by each set of wheels. So, for this wheel 1 we have the weight that is being carried as 33.8, and for wheel 2 we have 31.2. So, we have the rolling resistance as 33.8 times B by R plus 31.2 times B by R. We know the radius of the wheel as well as the coefficient of rolling resistance, from which we find the total rolling resistance as 0.1040 kilonewtons. And since this value is less than the traction force, which we have found to be 0.325 kilonewtons, the vehicle will indeed move. We will see one more example. So, here you see a roller thrust bearing, where between these two discs we have a series of rollers which are used to support. The rolling resistance is generally less than the bearing resistance in thrust bearing without rollers, and so they are generally preferred. So, let us see, in this problem we have the mean radius of these balls as 30 mm and the diameter of these balls are 10 mm. It has to support a load of P, and in order to keep this shaft in the rotation we need to apply this torque T. So, we are interested to find if the coefficient of rolling resistance is 0.127 mm and the various other dimensions are given, we are interested to find this value of the torque required to keep the shaft in rolling motion. So, when the shaft is idle, let us consider one of the balls. So, we have the reaction coming from the ground as R2 and say the reaction coming from this top face as R1. They lie in the same line, and this total of all this R1 or the vertical reactions of these various balls should be equal to this load P. So, in a limited equivalence, because all these forces are having the same direction cosine with respect to W, we can sum all these vertical reactions and say that that is R1, and sum of all the vertical reactions from this ground as R2, and they will be like this. But when the shaft starts to rotate in the counterclockwise direction, so this point of contact for the ball shifts to a new location in the forward direction. This is for the bottom surface. So, this reaction shifts to a point, the distance to which it moves is equal to the rolling resistance, that is 0.0127 mm in this case. So, the force coming from the top face, which is R1, is also displaced by a distance of 0.0127 mm. The radius of this ball bearings is 5 mm, and if we draw the free body diagram for the top portion, this is R1, we have P, the applied torque T, and this R acts at a distance of 30 mm. So, this is a limited equivalent diagram, because these all the forces R1 of the various balls have the same direction cosine with respect to the vertical. So, from this free body diagram we can write the equations. We have sin theta as the rolling resistance divided by the radius of the balls, from which we can find theta as 0.1455 degrees, and when we write the force summation equation for this shaft, we have sum of the vertical forces as minus P plus R1 cos theta equal to 0, and when we sum the moments, it is equal to T minus R1 sin theta times 30 equal to 0. So, from this we can find that the torque T that is required is 0.190 Newton meter. So, this example illustrated how we solve for rolling resistance